Well, welcome back to our class on discrete mathematics as we continue to talk about discrete structures, focusing primarily looking at a computer science application. And we've covered a lot of interesting information from Rosen. And for this is going to be the second to the last chapter that we'll go into. And we're going to be talking about Boolean algebra. So some of you may have some familiarity. Maybe some folks have had some circuits, digital circuit training, or maybe working with an Arduino kit or something like that. And so some of the things that we're going to cover here will be a little bit of a reminder for those. Otherwise, we'll get a chance to get some decent introduction to what Boolean is all about. So we'll talk about Boolean functions. We'll look at how we can do representing Boolean functions. And finally, what I think is the most interesting part is the logical gates, where we can actually construct circuits that follow the Boolean type of algebra, the functions that we're trying to create from them. Okay, well, let's get into some of the basics here. We'll first talk about Boolean functions. And so we'll give an introduction to Boolean algebra. And so basically we're using the word algebra intentionally. And so we have a Boolean way of looking at algebra. We'll look at Boolean expressions and Boolean functions, identities of Boolean algebra, duality, and the abstract definition of a Boolean algebra. So it'll be fairly straightforward. Maybe a few things that you'll have to get familiar with the syntax, but that's been true in a lot of the areas of Rosen when we're looking at number theory and how we're applying it for discrete mathematics. So Boolean algebra provides operations and the rules for working with the set of 0 and 1. In other words, binary. Electronics and optical switches can be studied using the set and the rules of Boolean algebra. The three Boolean, the three operations in Boolean algebra that we will be using the most are the complement, the sum, and the product. And I'm used to calling the inverter, the and or, but we'll get into that in a few minutes. And so this slide will help us to see that. So we have there's the sum, the product, and the complement. The complement, you can be thinking of it as an inverter. When we look at some of the circuits in a little bit, that'll make sense. The sum, this would be an or, and the product would be an and. And so the only way that you can get a true output is that both of the inputs are true. That would be for an and. And for a sum, you have to have one of them true for the output to be true. And the complement is whatever is on the input, you complement it. And so 0 would go into 1 and 1 would go into 0. So that's a little bit of a sense of how that works. So we can have Boolean expressions and Boolean functions. And so we can have a variable. And so here we can see an example of a function where we're seeing this relationship between the inputs and the outputs. And so when both of them are 1 or both of them are 0, we get a true on the output for this particular function. And that just gives you an idea of what that would look like. We can also find the values of more complicated things. And so here we have this function of x, y, and z, where it's x times y plus the inversion of z. So I'm just using the terms that they like to use here, sum and products and complements, to describe that. So we can just gradually put that together, and we can put x times y. And so we can get that result. We can get the inversion of z, and then we put those two together, and we can get that final result. So we have these interim products, and then we get the final product of putting that all together as we see there. Here's a couple other definitions of Boolean functions. F and G of and variables are equal if and only if f of b1, b2 up to bn is equal to g of b1, b2 up to bn, where b1, b2, bn belong to b, two different Boolean expressions that represent the same functions are equivalent. And you can be showing equivalence with this kind of a table. That's something that we'll get a chance to be thinking about as we move forward. The complement of the Boolean function f is the function f naught, where f naught of all of those is equivalent to the inversion of the whole thing. Let f and g be Boolean functions of degree n. The Boolean sum f plus g and the Boolean product fg are defined by fg of this gives that, and the multiplication fg is equal to the individual parts of that. So that just gives some things that are reminiscent of regular algebra, and we'll see some more expressions that help us along that line in a few charts. So how many different Boolean functions of degree n are there? And so here is a table that can help us that by the product rule for counting, there are 2 to the n different n tuplets of zeros and ones, because a Boolean function is an assignment of 0 or 1 to each of these different n tuplets. By the product rule, there are 2 to the n different Boolean functions of degree n. The example tells us that there are 16 different Boolean functions of degree 2, and we display these in table 3 as we see below. And so we have this table that goes into details here. Degree 1 is 4, degree 2 is 16, and we can see that was laid out there in table 3. Here are some identities of Boolean algebra. And you'll see that some of these are familiar, things that you have seen in regular algebra. There's also things called the De Morgan's laws. We had a chance to be introduced to that previously, and so now we're going to be utilizing them as we get into Boolean and as we look at circuit development, all of that. And so these are the list of the different identities and what it would look like in their Boolean algebra form. So I'm not going to walk through some of these examples, but we talked about this earlier. So how you solve something like this, you have the inputs, you put the interim products together, and then you finally come up with an answer. And this is the way that we can show that they're identical. And you show it's identical by having this table. And since there's a 1-for-1 correspondence between this and that, they're equivalent. And so that's the way that we go about proving it. So here's a formal definition of Boolean algebra. And so Boolean algebra is a set B with 2 binary operators, the and the or, elements 0 and 1, and a unitary operator, which I like to call the inverter, such that for all x, y, and z and b, we get the following. So you can look over those. I'm not going to read those, but those give you some insight there. Identity laws, complement laws, associative laws, cumulative laws, and distributive laws. All right, next let's get into representing Boolean functions. And so we'll talk about the sum of products, expansions, and functional completeness. The 2 important problems of Boolean algebra that will be studied here, the first problem is, given a value of Boolean function, how can a Boolean represent a Boolean expression that represents that function be found? This problem will be solved by showing that any Boolean function can be represented by a Boolean sum of Boolean products, other variables, and their complements. The solution of this problem shows that every Boolean function can be represented using the 3 Boolean operators, the multiplication, addition, and the inversion, the complement, however you want to call it. And we got a chance to be thinking about that already. The second problem is Is there a smaller set of operators that can be used to represent all Boolean functions? We will answer this question by showing that all Boolean functions can be represented using only one operator. Both of these problems have practical importance in circuit design. So we can do optimization of circuits, and we can be using some simple operators to put that all together. So here's an example. Find the Boolean expression that represent the function f of x, y, z and g of x, y, z that's listed here in the table. So now we're going the opposite direction where we're given the table, and now we want to be finding these expressions. And so the first one for f is x, the inversion of y, z, and for g, it's x, y, z, z bar, x bar, y, z bar. I'm not going to walk through how we go about doing that in detail, but there's various ways that you can be using it, as well as tools that can help you along that line. So we can go back and forth, and we've got a chance to be seeing how that would work, and we'll continue to be thinking about that here. So a literal is a Boolean variable or its complement. A midterm of the Boolean variable x1, x2 to xn is a Boolean product xy, x2, xn, where xi equals to xi, or xi is equal to the inversion of xi. Hence, a midterm is a product of n literals with one literal for each variable. And another definition, the sum of midterms that represents a function is called the sum of products expansion, or the disjunctive normal form of that Boolean function. So here's an example. Find the sum of products expansion for the function fyz. F of x, y, z equals to the quantity x plus y quantity z bar. And so we can be figuring that out. And so you can be seeing as the solution here and look at the table to help you get some sense of how that all works. We use Boolean identity to define the disjunctive normal form of f of x, y, z. And so this was the first part. And this is continuing on in terms of the solution. We use the distributive law, the identity law, unit property, distributive law, and idempotent law, all of that to help us to come up with a solution. Because every Boolean function can be represented using the Boolean operators multiplication, addition, and inversion, we say that this set is a functionally complete set. There's also a couple other things that are functionally complete, and you can be reading what they have here to be thinking that through as well. But let's just focus on this as the primary way that we're going to be looking at how we can be representing a Boolean function of however complicated we want to have it. We can make that work for us. Okay, next let's get into looking at logical gates. We'll give an introduction to them, how we can combine those gates, and then examples of the circuits that they can produce. Boolean algebra is used to model the circuitry of electronic devices. Every input and each output of such a device can be thought of as a member of the set 0, 1. A computer or other electronic device is made up of a number of circuits. Each circuit can be designed using the rules of Boolean algebra that we're studying in section 12.1 and 12.2. The basic elements of circuits are called gates, and were introduced in section 1.2. Now we'll get a chance to think about them in a little bit more depth. Each type of gate implements a Boolean operation. In this section, we will define several types of gates. Using these gates, we will apply the rules of Boolean algebra to design circuits that will perform a variety of tasks. The circuits that we will study in this chapter give output that depend only on the input and not on the current state of the circuit. In other words, these circuits have no memory capabilities. Such circuits are called combinational circuits or gating networks. So here are some illustrations of what those gates looks like, and we saw those earlier, but now we're going to be thinking about them in more detail. So we can construct circuits using gates, which take as an input the values of two or more Boolean variables and produce one or more bits as outputs, and inverters, which take the value of the variable as an input and produce the complement of this value as output. And so this is what I'm used to using these terms, the inverter for, and this is what it's shown looks like, the OR gate. And this is the equivalent in terms of a logical expression. And the AND gate, so this is addition, this is multiplication, and this is the complement. You can also have multiple inputs going into an AND gate or multiple inputs going into an OR gate. Those are other possible ways that you can be looking at this. Or there's a way that you can break it up into these and you just have multiple ones, two at a time that you add, and then the output of one gate feeds into another gate. And so this is a higher level representation trying to capture that concept. Then we can have these combinatorial circuits can be constructed using a combination of inverters, OR gates, and AND gates. We have two examples over here. The gates may share inputs, and the output of one or more gates may be input to another. And so what this squiggly line is, if you've never seen this kind of a circuit diagram, this means is that these two wires don't touch. And when you have this solid dot, that means that they do. And so this means that X flows into the input of that AND gate, and this X also flows into this inverter here. And so it produces X bar. Y goes into this input and Y goes into that output, just to give you an idea. So this is how we showed there's actually two ways that we can construct a circuit of XY plus X bar Y. And so you can see that they're really the same circuit. The only thing is that we're having a slightly different syntax for this. Here are some other examples of circuits that you can produce. And so I won't go through these in detail, but you can feel free to pause the video and look at these and get familiar with these. If any of you have played with an Arduino unit, one of the things that's interesting is to start to be thinking about how you can be utilizing digital gates of this sort, and let's start to do some programming. And you can actually do this either in software or hardware. And so depending on how much hardware you have, you may want to be choosing an equivalent that you could be doing in assembly language, which is also interesting to get some insight how that works. I do have a course on computer architecture that also gets a chance to do some introductory introduction to assembly language, and so you can think about that. Okay, just have a couple more charts, and this will be the last concept that I'll talk about. And so we talked about AND gates, OR gates, and inverters. Now we'll talk about adders, half adders, and full adders. And so this is now getting into something that's important that you would want to have in a computer. So logic circuits can be used to add two positive integers from their binary expansion. The first step is to build a half adder that adds two bits together, but which does not accept a carry from a previous adder. Since the circuit has more than one output, it is a multiple output circuit. So if you add 1 plus 1, you actually get 1, 0, which is a carryover. And that's what we're showing here. 1 plus 1 equals 1, 0. And then the regular output is 0. If you only have one of them, is 1, then the output is 1. And if you don't have, you have a 0 on both, and both the output and the carryover are 0. So this is, you need to be computing the different ways that you can get a carryover. And thus we can see that we have the logic for creating a half adder. Well, now that we have a half adder, we can save some time and just have this be a black box. And we're showing 2 of those black boxes with half adders. Now we have a carry in and we have a carry out. So that's what we're showing with this. And so we have the carry in, CI, and the carry out, CI plus 1. The inputs, and we have the output. So this is what a full adder is like. And so we have 2 half adders and a OR gate to complement the hardware that we would be using for all of that. And so let's say if we wanted to be adding 3 bits, this gives an example. But so a half adder and multiple full adders can be used to produce the sum of n bit integers. So this is with 3. So we have 2 full hours of half adders and 2 full adders and a half adder. And if we wanted to do more, then we're just going to be adding more full adders to get that sum. So say if you wanted to have 8 bits, 16 bits, 32, or 64 bits. Okay, well, that's all we have for this one. A little bit shorter lecture, but not at all meaning that this is not interesting and valuable. So take care. Bye-bye.